Glencore's metal recycling operations involve advanced multi-step processes designed to maximize recovery and purity of critical metals. The workflow begins with material inspection, sampling, and classification, ensuring that only suitable streams proceed to processing. Shredding reduces the material to uniform particle sizes, allowing precise separation of metals and non-metallic components. Subsequent smelting occurs in high-capacity furnaces at temperatures up to 1,200 degrees Celsius. Copper recovery, for example, is achieved through staged melting in 4 sequential furnaces, with each stage refining metal concentration from 25% to 98%. Resulting copper anodes, each approximately 300 kilograms, are sent to electrochemical refineries where they achieve 99.99% purity. Similar processes apply to nickel, cobalt, and precious metals, such as gold, silver, platinum, and palladium, ensuring high-value recovery for reuse in industrial applications. Lithium-ion battery recycling requires specialized procedures. Batteries are disassembled, and active materials are extracted in controlled environments to recover metals safely. Shredding, sieving, and separation systems isolate cathode, anode, and casing materials before smelting or chemical treatment. Advanced diagnostics and monitoring equipment are integral to quality control. Real-time sensors, sampling points, and hydrophones monitor process parameters, including temperature, pressure, emissions, and metal yields, ensuring consistent recovery while minimizing environmental impact. Finally, recovered metals are cast, extruded, or processed into standard industrial forms for reuse in energy storage, electronics, and manufacturing supply chains. The integration of precision shredding, controlled smelting, separation technologies, and real-time process monitoring exemplifies Glencore's technical leadership in sustainable metal recycling. The Senebogen 813 OEQ balancer at Schultz Recycling in Germany operates as a high-efficiency material handler engineered specifically for continuous feeding of heavy-duty shredders. Its equilibrium counterbalance system reduces energy demand by up to 75%, allowing the machine to work long cycles with minimal power draw while maintaining full lifting capacity. The 8130 EQ uses a rigid, rail-guided boom structure that delivers precise, vibration-free positioning of scrap loads, even at extended reach. Equipped with an electric drive, large format slewing ring, and high-flow hydraulics, the machine sustains smooth, repeatable motions critical for consistent shredder loading. Its elevated operator station provides a clear line of sight to infeed conveyors and sorting zones, improving control and safety. Heavy steel undercarriage components and reinforced boom joints ensure durability under extreme recycling conditions, where continuous loading, dense scrap handling, and long duty cycles are standard.
The NKMZ 6300 hot forging press, manufactured in 1981 in Ukraine, is a robust machine designed for heavy forging operations with a rated capacity of 6,300 tons. It features a slide stroke of 460 millimeters and can perform up to 40 strokes per minute continuously, enabling high productivity. The press has a shut height of 1150 millimeters with an adjustable clearance of 15 millimeters between the slide and table. The working table measures 1,600 millimeters left to right and 1,900 millimeters front to back, while the slide dimensions are 1,680 millimeters by 1,680 millimeters. Top and bottom ejectors provide strokes of 100 millimeters and 230 millimeters respectively to facilitate part removal. Upright openings measure 1,100 millimeters in width and 1,250 millimeters in height, with a clear distance of 1950 millimeters between uprights. Powered by a 400 kilowatts main motor, The press's overall dimensions are 8,600 millimeters long, 5,900 millimeters wide, and 9,300 millimeters high above floor level. Weighing 658 tons, it is engineered for demanding industrial forging applications. In May 2020, Prevny Brnenska Kavarna presented an insightful look into the closed die forging process at the historic forging plant of Poldy Kladno. The focus was on conventional forging operations using classic drop hammers, a method still essential in the production of robust, high-precision steel components. The process begins with billets being heated to forging temperature in a gas-fired furnace. Once the metal reaches optimal plasticity, it is extracted and undergoes an initial preforming stage on a traditional drop hammer. This step ensures the billet is shaped into a rough form that will properly align within the die cavity. To further improve the billet's fit, operators manually bend the hot material, preparing it for precise die closure. The billet is then placed into the lower half of a closed die, mounted on a counter-blow drop hammer. Once in position, forging begins as the upper die repeatedly strikes with high force, driving the material to fill the entire cavity. After forging, the resulting component includes excess flash, material that escapes along the die parting lines. This surplus is trimmed off using a powerful trimming press, ensuring clean edges and dimensional accuracy of the final forging. The demonstration at Poldy Kladno highlights not only the technical expertise required in manual forging, but also the continued relevance of traditional hammer forging in modern metalworking applications. At Kavarna Viva, forging excellence begins with precision engineering. Utilizing advanced 3D CAD/CAM software and simulation tools like NX11 and Forge, engineers design optimized forming processes tailored to complex customer requirements. Tooling is crafted on high-speed CNC machining centers using vacuum-hardened, nitrated materials, ensuring production stability. Forgings from 0.1 to 30 kilograms are made from various steels, including micro-alloyed grades, on 12 automated press lines. Induction heating guarantees controlled thermal treatment, followed by blasting, calibration, and inspection. Quality is assured with state-of-the-art control systems, 3D Zeiss metrology, spectrometry, micro-hardness testing, and flaw detection instruments. At forged steel crankshafts used in heavy-duty engines undergo a highly specialized and energy-intensive manufacturing process, combining massive forming forces with precise thermal and mechanical treatment. The operation begins with high-grade steel billets, which are preheated to forging temperature. These billets are then subjected to forge rolling, a critical deformation step that elongates and compresses the material to begin forming the crankshaft's main contours, optimizing its grain structure for enhanced strength and fatigue resistance. The semi-formed workpiece is next transferred to a 12,800-ton screw press, which delivers immense impact energy to create the precise geometry of the crank webs, pins, and journals. The forging operation ensures material consolidation and structural integrity throughout the part. This fully integrated process chain results in a forged steel crankshaft capable of withstanding the high loads and stresses of modern heavy-duty diesel and gas engines, offering superior performance, long fatigue life, and uncompromising reliability in demanding applications such as marine propulsion, mining equipment, and industrial power systems. Following this, the crankshaft enters the 2,500-ton hydraulic trimming and calibration press, where excess flash is removed and dimensional tolerances are refined to meet strict OEM specifications. After forming, the crankshaft undergoes a controlled cooling process. This carefully managed thermal treatment relieves internal stresses, refines the microstructure, and enhances hardness without inducing cracks or distortions. Once cooled to a specific range, the crankshaft moves into the automated warm straightening operation, where hydraulic rams correct any minor warping under monitored thermal conditions, ensuring optimal alignment across all bearing surfaces. The built-up H-beam manufacturing process begins with detailed shop drawing preparation using Tekla software. The nesting process optimizes material usage, followed by inspection of incoming plates and dimensional verification. Tensile testing ensures the raw material meets mechanical requirements. Plates are cut to size and shape, then assembled into H-sections. Submerged arc welding joins the flanges and web, with straightening and mechanical correction applied to eliminate flange distortion. Dimensional inspection is conducted, followed by comprehensive, non-destructive testing, NDT, including visual, ultrasonic, magnetic particle, and dye-penetrant testing. During fitting, qualified welders assemble the components, and fit-up inspections confirm accuracy. Final quality checks ensure dimensional tolerance, proper orientation, and weld integrity. Rust removal is achieved through automated shot blasting, accommodating sections up to 3,000 mm in height and 2,500 mm in width. Surface roughness is then inspected. The painting process is executed with precision, and coating thickness is verified. After passing all inspections, the finished H-beams are staged and prepared for delivery. In South, the SANY Smart Factory for truck-mounted concrete pumps features a fully automated production line ensuring precision and efficiency. Unmanned blanking and automatic sorting systems manage raw material preparation. Robotic welding ensures consistent joint quality, while unmanned CNC machining achieves high dimensional accuracy. Components proceed to an intelligent paint shop for uniform coating and corrosion protection. Finally, the streamlined assembly line integrates all parts with minimal human intervention. This smart manufacturing approach enhances productivity, reduces errors, and ensures reliable, high-performance concrete pumps ready for demanding construction applications. The die-bend cambering on the R16S, the world's largest section bending machine located in Cosley, West Midlands, involves a highly controlled process. After loading the beam, measuring locations are precisely set. The bending operation begins with an initial load, gradually increased to achieve the required camber. A pulling unit maintains constant tension on the beam, ensuring accurate deformation without distortion. This advanced machine handles large structural sections with exceptional precision, supporting critical applications in construction and heavy industry. The process ensures consistency, dimensional control, and structural reliability, even for the most demanding cambering requirements. The Melco pulley plant follows a rigorous and precise manufacturing process to ensure high-quality pulley production. It begins with advanced design and engineering, followed by plate rolling to form the shell. Longitudinal sub-arc welding ensures strong, uniform seams. Disc and shaft machining are performed to precise tolerances before pulley assembly. Circumferential sub-arc welding then secures the end discs to the shell. Each pulley undergoes non-destructive testing to verify weld integrity. Outside diameter machining ensures accurate final dimensions. The lagging process improves traction and durability. After painting, bearing fitment and greasing are carried out with precision. Finally, pulleys are protectively packed and dispatched for delivery. Cold Rolling Mill Number 1 and Number 2 at Attica Steel are state-of-the-art facilities designed for the precision processing of hot-rolled steel into high-strength cold-rolled coils. Mill Number 1 focuses on ultra-thin gauges with high surface quality, while Mill Number 2 handles medium to heavy gauges with consistent mechanical properties. Both mills feature 6 high mill stands, automatic flatness and thickness control systems, and computerized process monitoring. The lines include degreasing, tension leveling, and recoiling sections to ensure optimal finish and performance. These mills support the production of premium steel for automotive, white goods, and construction sectors, reinforcing Attica Steel's position as a leading flat steel producer. From flat steel sheets to mirror-finished spoons and forks, have you ever wondered how everyday cutlery is crafted with such precision? Behind every polished utensil lies a meticulous, high-tech process that transforms raw stainless steel into elegant tableware used around the world. It begins in the raw material workshop, where high-grade stainless steel sheets are received and stored. The material is then sent for stamping and shearing, where hydraulic presses and cutting dies punch out flat blanks for different cutlery types, spoons, forks, and knives. Next, the rolling and pressing process refines the blanks to the required thickness and consistency. Using calibrated rolling mills, the stainless steel is shaped to achieve uniform density and strength. After pressing, edge trimming machines remove excess material to define a clean profile, ensuring dimensional accuracy before the forming stage. The forming phase is conducted using precision molds in high-tonnage presses. Here, the distinct shapes of the heads, bowls of spoons, prongs of forks, or blades of knives are molded. For multi-part utensils like knives, welding is done to join the blade and handle using automated head welding systems. Once formed, each item undergoes grinding and polishing. Automated polishing lines handle bulk finishing, followed by manual polishing for fine detailing and high-gloss surfaces. Surfaces are then cleaned using industrial ultrasonic washers to remove polishing residues and dust. Following the cleaning, items pass through a laser engraving station where brand logos or patterns are etched onto the surface using high-precision fiber lasers. This non-contact process ensures durability and aesthetic clarity. Quality inspection and packaging come next. Trained inspectors check each item for surface finish, dimensions, and welding quality. Approved products move to the packaging area, where they are grouped, boxed, and labeled according to client or market specifications. Throughout the entire process, tool and die maintenance is conducted in a dedicated mold workshop, ensuring every stamping and forming die maintains performance tolerances. In conclusion, stainless steel cutlery manufacturing is a complex integration of stamping, forming, welding, polishing, and laser technology, delivering products that combine strength, hygiene, and elegance for use in households and hospitality worldwide. The SIM-PAC hot stamping line enables ultra-high strength steel forming, producing lighter yet significantly stronger components. This advanced process, featured in the Genesis GV80 with over 17% hot stamped parts, exemplifies safety-driven innovation in automotive engineering. The die bending process used in Hakama Schweitz's sheet metal housing fabrication ensures high precision and repeatability. Sheets are positioned between a punch and die, then bent under controlled pressure to achieve the desired geometry. The CNC-controlled press brakes allow for consistent bending angles, crucial for complex enclosures. Material springback is compensated via software calibration. The process enables sharp edges, tight tolerances, and excellent dimensional stability, supporting downstream assembly. Hakama's integration of automated handling improves throughput and maintains uniform quality in serial production of sheet metal housings. TechnoStamp special press brake tooling is used for precision sheet metal bending in custom or complex applications. Its primary function is to form metal parts with specific angles, radii, or shapes that standard tooling cannot achieve, such as deep channels, tight bends, or scratch-free surfaces. TechnoStamp special press brake tooling is designed to work with various types of press brakes, mechanical, hydraulic, electric, and servo hybrid, depending on the application and desired part geometry. Each machine type enables different forming capabilities. The manufacturing process starts with selecting high-strength alloy steel, followed by CNC machining to create precise geometries. These tools are tailored to specific machines and part requirements, ensuring accuracy, repeatability, and minimal tool marks during forming. TechnoStamp special tooling is essential in industries requiring high-quality custom bending, such as automotive, aerospace, and industrial equipment. The special tool, Omega, is a precision-engineered press brake tool designed for forming omega-shaped profiles with high dimensional accuracy. Manufactured from high-strength alloy steel and subjected to heat treatment and surface hardening, it ensures durability and minimal tool deflection under load. The tool geometry is optimized to reduce springback and material deformation. The special tool radius U-channel is designed for smooth bending of U-shaped profiles with large radii, ensuring minimal material stress and consistent results on various press brake machines. The special tool set metal clamp is a custom press brake tooling solution designed for forming integrated clamp features in sheet metal. Features two differently shaped ends designed to form interlocking clamp profiles. Staged bending with a rotating die allows for gradual, precise bending of complex profiles by rotating the die in steps while simultaneously pressing in the middle to form a balanced shape. In South Africa, SIMPAC completed a major technical achievement by installing 13 mechanical press machines, 1 transfer automation system, and 2 coil feeder units in a single project. Despite global challenges, including COVID-19, disrupted logistics, and a port fire that forced rerouting, SIMPAC maintained strict production and installation timelines. Each press was precisely aligned and integrated into an automated production line, with servo-controlled coil feeders ensuring consistent material flow. The transfer automation enabled seamless part movement, enhancing throughput and operational efficiency. Advanced control systems synchronized all units, while on-site commissioning ensured safety, accuracy, and full functionality. This project highlights SIMPAC's expertise in press line integration under highly demanding industrial and logistical conditions. From a simple sheet of stainless steel to a high-tech cooling giant, how is a milk tank born? A milk tank begins as flat, stainless steel sheets, transformed at Muller's advanced facility in the Netherlands. Laser-welded template evaporator panels are created to circulate refrigerant and rapidly cool milk. These panels are shaped, welded, and inflated for optimal thermal performance, minimizing energy transfer between inner and outer shells. Piping, agitators, sensors, and control units are then added. Rigorous quality checks ensure hygiene and long-term reliability. Tanks are cleaned, tested, and transported, like this batch headed to Ireland. On-farm installation is handled by trained Muller partners like Kingston Refrigeration. Tanks range from 1,700 to 50,000 liters, tailored to farm needs and space. From sheet metal to high-tech cooling, Muller crafts durable tanks to protect the world's milk supply. What if a simple dip could make steel nearly immortal? Galvanizing is a protective process that coats steel with zinc to prevent corrosion. The most effective method is hot dip galvanizing, where steel is immersed in molten zinc, forming durable zinc-iron alloy layers that bond to the base metal. This coating resists abrasion and protects even when scratched. Valmont Coatings has specialized in galvanizing for over 50 years, offering eco-friendly solutions with 100% recyclable zinc. The hot dip process involves 3 steps: surface preparation, galvanizing, and inspection. Cleaning stages include degreasing, pickling, and fluxing. Once cleaned, steel is dipped into molten zinc, forming durable, corrosion-resistant coatings. The final visual inspection ensures full coverage and compliance. It's efficient, sustainable, and ensures long-lasting structural integrity. Electropolishing is a precision electrochemical finishing process that removes a thin layer of metal from stainless steel surfaces, enhancing both functionality and appearance. This controlled removal eliminates microscopic imperfections, sharp edges, and embedded contaminants while simultaneously passivating the surface. The operation commences pre-cleaning to eliminate machining oils and residues, followed by immersion in an electrolyte bath, typically a blend of sulfuric and phosphoric acids. A positive current is applied to the part anode, while negative cathodes facilitate ion removal. This results in a microscopically smooth, corrosion-resistant, oxygen-enriched surface ideal for critical industries like medical, food, and aerospace. C&H Bearings China ensures precision through multiple quality inspections. Gothic arch groove and bore tolerances are checked during processing. High-performance grease is filled under controlled conditions. Clearance and LFR track roller raceway tolerances are verified before assembly. Contour and surface roughness are inspected, followed by final laser marking. At SR Engineering works indoor, an automatic chain welding machine is actively welding individual chain links. The machine uses resistance welding technology, generating heat by combining electrodes and base metal to fuse the links. Ideal for mass production, it ensures uniformity in small-sized chains. It can weld a wide range of chains, from high-grade lifting chains to standard decorative. The spring grinding process at Betts Spring uses FS8 and Bennett grinders for precision grinding. FS8 handles springs 3/4 inch to 4-inch long with a single grind wheel, while Bennett grinders process 4-inch to 24-inch springs using dual wheels for accurate square-end results. The 3 to 8 mm pneumatic wire mesh welding machine is a high-performance system equipped with spool feeding, loop, and stacking units for efficient mesh production. It handles wire diameters from 3 mm to 8 mm, with mesh widths up to 2,500 mm and lengths up to 6 meters. The process begins with 1-ton payoffs and a first wire straightening unit, followed by synchronized feeding and looping. Cross wires are delivered precisely by the cross wire feeder. The welding unit operates at speeds of 80 to 100 welds per minute. Servo motor pulling ensures accurate mesh advancement. The system includes a mesh cutting and falling unit and a stacking unit for final product handling.
TV channel. Founded in 1950 and relocated to a state-of-the-art facility in Apaseo El Grande, Guanajuato, IMEM Transformadores Internacionales designs and manufactures distribution transformers, engineered for high productivity and lifecycle profitability. Each order begins with customer-specific specifications. Engineering generates electromagnetic and thermal models, then production fabricates hermetically sealed tanks via CNC shearing, robotic welding, and epoxy polyester coating. Precision winding machines produce copper or aluminum coils, while step-lap core cutters assemble low-loss grain-oriented silicon steel cores. Final assembly integrates bushings, tap changers, and accessories, followed by vacuum oil impregnation and heat curing. Routine, type, and special tests per ANSI Fire IEEE validate dielectric strength, no load losses, and temperature rise.
Technorulli specializes in precision engineering and automated production of rollers and pulleys for conveyor systems. The facility integrates CNC lathes and automatic balancing machines to ensure micron-level tolerances, critical for high-speed applications in logistics and airport handling systems. Each roller undergoes controlled manufacturing cycles, including machining of bearing seats, press fitting, and dynamic balancing. Pulleys and return drums are produced with optimized crown profiles to maintain belt alignment and reduce wear. The manufacturing line supports both steel and polymer rollers, with tailored solutions for load-bearing capacity, noise reduction, and low-friction operation. Automated warehouses enable real-time material flow, supporting just-in-time production. Robotic arms assist in repetitive handling, ensuring consistent quality and reducing human error. Each unit is subjected to dimensional verification using digital measurement systems. For motorized rollers, the integration of motor housings and thermal dissipation structures is CNC machined for tight fit and enhanced durability. With over 60% of production energy sourced from renewables, Technorulli's facility adheres to strict energy efficiency protocols. The result is a scalable, high-performance product portfolio capable of withstanding the mechanical stresses of continuous duty environments while ensuring minimal maintenance and extended service life. At Reimer, the investment casting process begins with the creation and CNC machining of precision dies. These dies form the wax patterns, which are produced under strict temperature control to ensure dimensional accuracy and surface detail. The wax patterns are then assembled onto trees and moved to a robotic dipping station, where they are coated with layers of ceramic slurry. Each layer is dried before the next is applied, forming a robust shell. After dewaxing, the ceramic molds are stored carefully to minimize handling damage. Prior to casting, alloys are analyzed using the Bruker Q2 metal spectrometer to confirm exact chemical composition. Molten metal is then poured into the ceramic molds under closely monitored temperature conditions. After solidification, the ceramic shell is knocked out using pneumatic hammers, and castings are separated from the trees. Final operations include cleaning, grinding, inspection, and CNC machining, such as milling, turning, and tapping, to complete the finished component.
GEASRL operates across multiple industrial sectors, including automotive and energy. Their product range includes engine components, automatic valves, motorcycle swing arms, and primarily aluminum flanges, which represent the company's core business. In the aluminum foundry, the production process begins with alloy preparation and purification. Operators perform degassing by introducing a metallic sodium tablet into the molten aluminum, effectively removing air and preventing microporosity in the cast parts. Precision in timing and pouring technique is critical when transferring molten aluminum into wax molds within the shell casting system, as this directly affects the integrity and yield of the final component. The foundry uses high-quality molds, referred to as maschietti superiori, to ensure accurate extraction and casting. Aluminum's recyclability is a key advantage, and all ingots used are sourced from certified recycled material, primarily of Italian origin, supporting sustainability and made-in-Italy quality standards. This approach guarantees consistent product differentiation and high-quality cast components for automotive and industrial applications. The RLX 780 dual-mode lathe combines full manual hand-wheel control with ProtoTrack RLX CNC for rapid one-off or batch work. A one-piece induction-hardened cast iron bed and 3 meters between centers deliver extreme rigidity, supporting 780mm swing-over bed and 160mm bar capacity. The headstock employs ground, induction-hardened Japanese gears, dual precision taper roller bearings, forced oil lubrication with pump and cooler, and a 2-range gearbox, giving 13 spindle speeds to 1,000 revolutions per minute and constant surface speed cutting. A 30-kilowatt spindle motor feeds a 500mm 3-jaw steel chuck. Optional 4-jaw or drilling attachments are available. Heavy tailstock locks at 2 points and glides on an air cushion for effortless repositioning. Dual interlocked guards enable safe open-door manual setup or fully enclosed CNC machining, while a front access chip tray simplifies cleanout in limited floor space.
Acura 65EL from HEDELIUS delivers high-speed, 5-axis dynamic machining with exceptional precision and automation capability. Designed for complex components, this compact machining center features a rigid gantry structure and an integrated rotary tilt table, allowing simultaneous multi-side processing with minimal repositioning. Its generous travel paths, 700mm on the x-axis, 650mm on y, and 600mm on z, enable flexible part handling across various industries. The powerful spindle reaches speeds of up to 18,000 revolutions per minute and supports rapid traverses of 40 meters per minute, minimizing non-cutting time. Tool holders are available in SK40, BT40, or HSKA63, supporting a wide range of cutting applications from aluminum to stainless steel and titanium. Automation is central to the Acura 65EL. On the left side of the machine, an open interface automation port allows seamless integration with robotic systems and pallet handling units like the Marathon P422 or P406. Up to 6 pallets can be clamped using pneumatic zero-point clamping, ensuring continuous, unmanned operation, ideal for high-mix, low-volume production and overnight runs. The machine is equipped with a Siemens or Heidenhain CNC control, offering live tool monitoring, advanced collision protection, and real-time process feedback. These features enable safe, efficient machining with high repeatability and reduced cycle times. With its capability for trochoidal milling, adaptive roughing, and simultaneous 5-axis finishing, the Acura 65EL is perfect for industries such as aerospace, medical device manufacturing, mold and die, and precision mechanical components. The machine also features a large tool magazine, expandable up to 329 tools, ensuring long autonomous operation without manual intervention. An integrated chip conveyor and coolant system support continuous operation, even in demanding environments. Vibration damping construction and thermal stability guarantee long-term accuracy. This machining center embodies a perfect balance of compact design, automation readiness, and high-performance 5-axis capability. From dynamic roughing to ultra-fine finishing, the Acura 65EL offers manufacturers increased productivity, reliable unattended operation, and top-tier machining quality, all in a single, fully integrated system.
WFL's MILLTURN machines enabled customers to efficiently program complex workpieces, including all gear features within a single system. Users can simulate the entire machining process, perform all operations, and measure the part directly on the machine. This integrated approach ensures high precision and reduces setup times, allowing for the production of perfect gear components in one seamless workflow. WFL's gearing solutions thus provide an advanced, exact platform for high-quality gear manufacturing. The manufactured dragline propel gear starts with raw materials, followed by welding and fabrication. It is machined on our Sheath VTL, then processed on our 8-meter gasher/hobber. The teeth are finished on the MAAG grinder, and finally, the gear is ready for painting and shipment. The
Brother M140X2 is a high-performance 5-axis CNC vertical machining center designed for precision milling and turning operations. It combines milling and turning functions in one compact machine, increasing efficiency and reducing setup times. The machine features a travel range of 200 mm X-axis, 440 mm Y-axis, and 305 mm Z-axis, with an A-axis tilt of plus 120 degrees to minus 30 degrees and full 360 degrees Celsius axis rotation. Its spindle reaches speeds up to 16,000 RPM, powered by a 10.1 kilowatts motor with a BT30 spindle taper. The turning spindle can operate up to 2,000 RPM. Rapid traverse rates up to 50,000 millimeters per minute enable fast machining cycles. Equipped with a 22-tool magazine and the Brother CNCC00 control unit, it supports complex multi-axis machining with high precision. The compact design fits various workshop layouts, ideal for aerospace, automotive, and medical industries. The M140X2 efficiently produces complex parts with tight tolerances, improving productivity and reducing the need for multiple setups or machines. Its advanced capabilities make it a versatile solution for demanding manufacturing tasks. The Okuma LB3000EX-MYW is a high-performance horizontal CNC lathe designed for precision machining of complex parts. It features a rigid slant bed construction and a high-torque M spindle, ensuring stability and accuracy during heavy-duty cutting operations. The machine is equipped with Okuma's thermo-friendly concept to minimize thermal displacement, enhancing machining precision over extended periods. The MYW configuration includes a Y-axis, W-axis, and sub-spindle, enabling multi-axis machining and reducing the need for multiple setups. With a maximum turning diameter of 470 millimeters and a maximum turning length of 1,300 millimeters, it accommodates a wide range of workpieces. The machine boasts a spindle speed of up to 6,000 RPM and offers rapid traverse rates of 25 meters per minute in the X-axis and 30 meters per minute in the Z-axis, facilitating efficient processing. The OSPP 500 LCNC control system provides intuitive operation and seamless integration with peripheral equipment. Ideal for industries requiring high precision and versatility, the LB3000EX-MYW excels in applications such as aerospace, automotive, and mold making. Tool Factory Cutting Tool Solutions GmbH produces high-performance ISO indexable inserts for turning operations. Their carbide substrates and advanced coatings ensure maximum material removal rates and extended tool life. The turning holders support triple coolant connections compatible with standard VDI holders, enabling precise coolant delivery directly to the cutting edge. This design optimizes machining efficiency and integrates smoothly with existing machine tool systems, enhancing productivity and tool durability in diverse manufacturing applications.
The Nergesa PP200 horizontal press brake delivers 200 kilonewtons forming force in a stiff 60 mm welded steel monoblock, enabling bend, flare, shear, punch, swag, or straighten operations on plate, bar, tube, and profiles. A mechanically guided hydraulic ram offers 250 mm stroke, 0.05 mm repeatability, and 10 mm S working speed, retracting at 35 mm S for high cycle rates. Quick change tooling, usually under 30S, accepts a broad catalog of optional dies. The supplied 4V matrix handles closed section bends impossible on conventional press brakes, and fixed radius inserts curve hollow tube to 180 degrees. Integrated storage keeps dies organized beside the 600 x 1170 mm work table set at 950 mm height. A 2.2 kilowatts motor drives a 27L hydraulic circuit on 234 hundredths of a volt 3-phase, giving plug-and-play installation. Weighing 625 kilograms, the PP200 is a compact, indispensable multi-process machine for metal fabrication workshops.
The production process of the cryogenic tank begins with incoming material inspection and metal marking. Next, rolling and welding of shells and installation of reinforcing rings are performed. The inner vessel, made of 12X18H10T steel, undergoes 100% X-ray inspection, hydraulic and pneumatic testing. After insulation, vessel assembly, and vacuuming, instrumentation and control devices are installed. Finally, the tank is primed, painted, and tested with cryogenic products. The sand mold making process begins with preparing a special mixture of clay, sand, sawdust, and binders to achieve the right cohesiveness and heat resistance. The molding sand is thoroughly mixed to reach optimal moisture content and plasticity. Next, The mold maker presses the sand mixture tightly around a pattern, which is usually made of wood or metal, replicating the shape of the desired casting. The pattern creates a cavity inside the mold where molten metal will be poured. Once the sand is packed firmly, the pattern is carefully removed, leaving a precise negative impression of the part. The mold is then dried or lightly baked to harden and remove excess moisture, ensuring it can withstand the high temperatures of molten metal. When ready, molten metal is poured into the sand mold through gating channels. After cooling and solidification, the sand mold is broken apart to extract the finished casting. Sand molds offer advantages such as ease of preparation, low cost, and suitability for producing large or complex parts in small to medium production runs. This traditional method remains widely used in foundries around the world for its flexibility and efficiency. At Arson Docum Corum, the shaping of molten iron starts with melting iron to exact temperatures, ensuring ideal fluidity for casting. The molten iron is poured into precision-engineered molds designed for single-piece castings, ranging from 3 kilograms up to 11,000 kilograms. The casting process involves controlled solidification to avoid defects and maintain dimensional accuracy. Advanced molding techniques and rigorous quality inspections ensure structural integrity. Handling large-scale castings, such as a 4-ton single piece, requires specialized equipment and skilled operators. The foundry's expertise in metallurgical control and casting technology allows for the consistent production of heavy, high-quality iron components tailored to industrial demands. The hydraulic billet shearing is a high-force cutting process used to divide hot or cold metal billets into precise lengths. Utilizing a hydraulic-driven blade, it ensures clean, square cuts with minimal deformation. Commonly used in forging and rolling mills, it enhances productivity, safety, and material utilization efficiency. The Metal Design manufactures precision cutting discs designed for high-performance metalworking applications. Their discs offer optimized durability and cutting efficiency across various ferrous and non-ferrous materials. The metal spinning process employed involves rotating a metal blank at controlled speeds, applying localized pressure with specialized tooling to form seamless, axisymmetric components. This method ensures dimensional accuracy, uniform wall thickness, and superior surface quality. Metal Design integrates advanced machining controls and quality assurance protocols to maintain tight tolerances and repeatability in both cutting disc production and metal spinning operations, meeting rigorous industrial standards. The Bailey Industrial RDB 350 tube bender bends 64.5x 3.5 mm mild steel tubing at its slowest bend speed, ensuring maximum control and precision for tight radius applications. The
Vayner Machinery armored cable cutting and stripping machine is designed for efficient processing of armored copper cables. It precisely cuts, strips, and separates insulation, enabling fast, accurate, and safe preparation of cables for recycling or further electrical applications, ensuring consistent quality and minimal material loss.